Hey class, and welcome back to another sample problem. So here's a uniform circular motion problem I wanted to kind of work through to give you some insights into the way these types of problems can be approached. So this example is about tetherball, which I don't know if you have ever played, but it's a fun game. Used to play it on the playground, and in fact, a few years ago, after I was an adult, I actually played it once with my brother, and it's amazing how different the game is as an adult. It's a bit more intense and kind of crazy. But anyway, so imagine you have a tether ball, which is basically a large ball shown here attached at some point to a ceiling. And what I'm going to do is try to figure out what the tension is in the string and what angle it makes. So the tension is labeled Ft, and then the angle is represented with beta, and what we're going to do is measure things that you realistically could measure. So for example, you could measure the length of the string, the mass of the ball, and the period, or the amount of time it takes to go around in its circular motion. And we're going to assume for now it's moving at a constant speed as shown here. We don't know exactly what that speed is. That would be harder to measure, but the period, the amount of time it takes to complete one revolution, would be easier to measure. So again, just so we know, things that we could really figure out, or givens, would be the length of the string, the mass, and then the period, the time it takes to complete one revolution. And what we want to figure out, what we don't know, is the force of tension in the string and that angle beta. All right, so what we want to do, we're thinking of force, so you should automatically think free body diagram. So here's my ball. If I'm going to draw a free body diagram, I'll go ahead and label some axes. So we'll call this the x direction and this the y direction. I'm going to draw my free body diagram as though it's like a freeze frame in the exact orientation it has in the picture. All right, so what forces do we have? Well, everything on Earth has a weight, so going down we're going to have mass times gravity, and then we also have the tension force acting at an angle here. And the question is, what is that angle? Well, if we look up here, we have a triangle that you can observe made by the string. So the hypotenuse is L, here is the angle beta, and then R is the opposite side there. So this angle here, which would really be 90 minus beta, would be the same as the angle here. And so therefore, by geometry, we can label this angle here as our angle beta. All right, so if we're thinking forces, we're going to be looking at doing some of the forces, right? Some of the forces in the x, and then some of the forces in the y. That's where you always want to think to go. So let's go ahead and break our tension force into x and y components. So the x component of that tension force is going to be the magnitude, and since it's x and beta is here, x would be this opposite side if we made a little triangle, right? So the opposite side is sine. So tension times the sine of our angle beta. Ooh, I almost said theta. Let's fix that. That looks really ugly. So sine of beta. And then if we do the y, that's going to be the adjacent side, so that would be ft cosine beta. All right, now if we come back to doing some of our forces, in the x direction, right, we're going to have a net inward acceleration, which is our centripetal acceleration since it's uniform circular motion. So what we're going to have then for some of the forces is we have ftx, and that's it, that's easy, equals m times that centripetal acceleration. In the y direction, now it's not accelerating or moving up and down at all, so therefore in the y direction the net force is going to be equal to 0. And so in the y direction we're going to have fty minus mg equals 0. All right, so let's go ahead and you can choose either of these two to pursue as you try to solve. You're not sure which one's going to help you solve the quickest, but we can look at either of them. Let's start in the x direction since it's first. We have ft times the sine of beta equals m, and centripetal acceleration we know is v squared over r. So first glance at this equation, oh boy howdy, let's see. We don't know ft or beta or v or r. None of those are our givens. M is the only thing we're given. That seems a little crazy. But wait, let's think about this a little bit more. ft and beta we know we want, but what is v? What is the velocity with which this is moving? Well, we're not given it, we can't measure it directly, but we do know, and we hopefully have observed for things moving in circular motion, that the speed at which they move is just the circumference of their circle, 2 pi r, over the period. And since the period is something that we know, we can insert this in for our velocity. So let's go back to our force equation here, and we have ft sine beta equals, oh, see, I didn't give myself enough space, so I'm going to erase this and try again a little further down so that I don't get so cramped, because my handwriting's bad enough without things being cramped. So we have ft sine beta equals m over r, and then v squared. So I'm going to just square each term in that, all right? So we have 2 squared is 4, pi squared, I'll just write pi squared, r squared is r squared, and then on the bottom we have t squared. All right, so one of our r's will cancel, that's a nice bonus, but we still don't know r. We're getting closer, but we don't know r, t, or sine beta. But let's think about r again. If we go back to our little triangle that we see over here, I'll just draw this again one more time. All right, you see the triangle here, we have L and R are 2 sides of our triangle. So we can observe that R is just equal to L multiplied by sine beta using our same trig functions that we're getting so used to. And oh boy howdy, I see something real neat. If I go to plug this in over here, I'll have sine beta on both sides of my equation, and it's going to cancel out. Oh yeah. So let's write that down. We have ft sine beta equals 4 pi squared m, and now instead of r, I'm going to write L sine beta, since that's what r equals. And then on the bottom, I have just the period squared, and check this out. My sine betas cancel, and I now have a solution to the question. What is ft equal to? Well, it's equal to 4 pi squared times the mass multiplied by L over the period that we can measure squared. That is most definitely a box-worthy answer. So bonus, we found what the tension is based on the 3 values we should be able to measure. So now the question is, what is beta though? How can we figure out beta? Let's look, okay, so we see it up here, but it got canceled out. Let's see, we see it over here, but we don't know what r is. Well, we haven't used our y equation yet. Let's see if that can help us figure out what beta is. So I'm going to scroll down here to give us a little bit more space, and I'm going to go ahead and just jump in where we left off in the y equation. So fty is ft cosine beta, mg is still mg, and that equals 0. So check it out, ft cosine beta equals mg, and so the cosine of my angle beta is just going to be equal to mg over the tension. All right, again, I'm running low on space, so let's scroll down some more. So we want beta. Let's plug in what we know the tension is. So let's plug this guy in down here. So cosine beta equals, so I have mg on top. Now since my tension is on bottom, that means I'm going to divide by the parts on top of my tension and then multiply by the things on bottom. So this is a little confusing algebra trick here, but since we're dividing, my t squared gets popped on top, and then the 4, the pi squared, the m, and the l all stay on the bottom. And if we look, our m's will cancel, and we take the inverse cosine of both sides. So beta is going to be equal to the inverse cosine of g times the period squared divided by 4 pi squared multiplied by L. And again, we have a box-worthy answer. So that's a pretty fun and pretty tricky one, but you see we walked through the process. We did some of the forces after looking at what we're given and had to use a few substitution and algebra tricks in there, but we found a net result, figuring out what our tension force is equal to and what the angle beta is equal to, all based on things that are easily measurable. So you could go and do this for fun, right? You know, have a little experiment in the backyard. But anyway, so hope that helps. Let me know if you have any questions. Otherwise, have yourselves a box-worthy day. And I'll talk to you next time.